Dear viewers, the title of my talk today is series solution of homogeneous linear differential equations. We know that a homogeneous linear differential equation can be solved by elementary methods, and its solutions are known functions from calculus like e to the power x, sin x, cos x, etc. However, if such an equation has variable coefficients, then it cannot usually be solved by elementary methods. Legendre's equation, hypergeometric equation and Bessel's equation are very important types of such homogeneous linear differential equations. Since they are quite useful in applied mathematics, we shall discuss the solution of Legendre's equation and Bessel's equation. First, we take up the case of Legendre's equation. There are two methods of finding solutions of such equations. The first is the power series method, and the second one is the extension of the power series method, that is the Frobenius method. Let us first discuss the power series method. This method gives the solution of the differential equation in the form of a power series. A power series can be used for computing the values of the solution, for exploring its properties, and for deriving other kinds of representations of the solution. A power series is an expression of the form sigma m equal to 0 to infinity a to am x minus x naught to the power m, which may be expanded as a naught plus a1 x minus x naught plus a2 x minus x naught whole square and so on, where a naught, a1 and so on are real constants known as the coefficients of the series. X naught is a real constant and called the center of the series. X is a real variable. Some familiar examples are e to the power x, which is sigma m equal to 0 to infinity x to the power m over x m factorial. We may write it as 1 plus x square by 2 factorial and so on. Another example is sin x, which is m equal to 0 to infinity minus 1 to the power m x to the power 2m plus 1 over 2m plus 1 factorial, which when expanded gives us the series x minus x cube by 3 factorial plus x to the power 5 by 5 factorial and so on. And then we can take the cos x function, which is sigma m equal to 0 to infinity minus 1 to the power m x to the power 2m over 2m factorial, or we may write it as 1 minus x square by 2 factorial plus x to the power 4 by 4 factorial and so on. The nth partial sum of the power series given by equation 1 is defined as Sn x equal to a naught plus a1 x minus x naught to the power 1 plus and so on an x minus x naught to the power n. The remainder of the power series given by equation 1 after n plus 1th term is defined as Rn x, which is equal to sigma r equal to 1 to infinity a n plus r x minus x naught to the power n plus r. That is, the first term will be a n plus 1 x minus x naught to the power n plus 1, then we will have a n plus 2 x minus x naught to the power n plus 2 and so on. These power series given by equation 1 is said to be convergent or divergent at the point x equal to x1 if the sequence of partial sums Sn x is convergent or divergent at the point x equal to x1. From the definitions of Sn x and Rn x, it is clear that for every n, Sx is equal to Sn x plus Rn x. If the series is convergent at x1, then we can say that for any epsilon greater than 0, there exists an integer and not belonging to n such that modulus of Rn x1 is less than epsilon for all n greater than n naught. If the set of points where the series converges is a finite interval, then its midpoint is x naught. Let this interval be mod of x minus x naught less than r. In this picture we have shown this convergence interval of a power series with center at the point x naught. The interval is x naught minus r to x naught plus r, where the series converges. The midpoint of the interval is at x naught. The number r is called the radius of convergence of the power series given by equation 1. The power series does not converge outside this interval. It may or may not converge for mod of x minus x naught equal to r. The value of r can be obtained from one of these two formulas. that is r equal to 1 over limit m tends to infinity mod of am plus 1 over am, or r equal to 1 over limit m tends to infinity mth root of mod of am, provided these limits exist and are not 0. If these limits are 0, then the series converges only at the center. Sometimes the series converges for all values of x, that is the value of r comes out to be infinity. So, in such cases the series will converge for all values of x. Sometimes the value of r is finite, then the series will converge in the interval mod of x minus x naught less than r. So, when the limits will be infinite, we will have the convergence only at the center. When the limits will be infinite, we will have the series converging for all values of x, and when the value of r lies between 0 and infinity, we will have the series converging for mod of x minus x naught less than r, that is in an interval. Now, for each value of x for which the series converges, it has a certain value s x, and so we can say that the series 1 represents a function s x. We may therefore write s x equal to limit sigma m equal to 0 to infinity am x minus x naught raised to the power m. Let us study some examples. First, we take an example of the series which converges only at the center. Let us take the example of the series sigma m equal to 0 to infinity m factorial x to the power m. We can write it as 1 plus x plus 2x square plus 6x cube and so on. Let us find the value of m plus 1 over m. It is equal to m plus 1, which we can see goes to infinity as m goes to infinity, and therefore, the series converges only at the center, that is x equal to 0. Such series are not of much practical interest. Next, we take an example of the series which converges in a finite interval. Let us take the case of a geometric series. For the geometric series 1 over 1 minus x, which can be expressed as 1 plus x square and so on, it turns out that the region of convergence, that is the interval of convergence, is given by mod of x less than 1, that is the interval minus 1 to 1, open interval minus 1 to 1, because here m is equal to 1 for all values of m, and therefore, if you apply the formula r equal to 1 over limit m tends to infinity mod of m plus 1 over m, or r equal to 1 over limit m tends to infinity mth root of mod of m, you find that r is equal to 1, and therefore, the series converges for all values of x in the interval minus 1 to 1 and represents the function 1 over 1 minus x. Next, we take an example of the series which has an infinite radius of convergence, that is it converges for all values of x. Let us take the example of the function e to the power x, which can be written as 1 plus x square by 2 factorial and so on. If we find here m plus 1 over m, it turns out to be 1 over m plus 1, which we see goes to 0 as m goes to infinity, and therefore, r is equal to infinity in this case, and so the series converges for all values of x. Now, let us study some properties of the power series. A power series may be differentiated term by term, that is, if the series 1 converges for mod of x minus x naught less than r, where r is greater than 0, then the series obtained by differentiating term by term also converges for those values of x, that is for mod of x minus x naught less than r. And you can see that when you differentiate the series given by 1, you get the series sigma m equal to 0 to infinity m a m x minus x naught to the power m minus 1, which is by dash x, and this series converges for mod of x minus x naught less than r, the region of convergence of the original power series. Next, we study how when we can add two power series. So, two power series may be added term by term, and the resulting power series converges in the interior of the convergence interval of each of the series. Thus, if sigma m equal to 0 to infinity a m x minus x naught to the power m and sigma m equal to 0 to infinity b m x minus x naught to the power m have positive radii of convergence and their sums are f x and g x, then the series sigma m equal to 0 to infinity a m plus b m x minus x naught to the power m converges and represents f x plus g x for each x that lies in the interior of the convergence intervals of each of the given series. The third property is the two power series may be multiplied term by term. The interval of convergence is the same domain as in the case of the addition of the series, that is the interval of convergence is the interior of the convergence intervals of each of the given series. The series obtained by multiplying the two series in 3 is obtained by multiplying each term of one series by each term of the other series, and thus we get the product as sigma m equal to 0 to infinity a naught b m plus a 1 b m minus 1 and so on a m b naught into x minus x naught to the power m, which converges and represents f x into g x. Now, lastly we discuss if a power series has a positive radius of convergence and a sum identically 0 in the interval of convergence, then each coefficient of the power series must be 0. We now define a real analytic function. A real function f x is called analytic at a point x equal to x naught if it can be represented by a power series in the powers of x minus x naught with radius of convergence r greater than 0. So, that is to say that we will call a real valued function f x to be an analytic function at a point x equal to x naught if we can represent it by a power series in the powers of x minus x naught with a positive radius of convergence. We next discuss the how to when can we find a power series solution of a homogeneous linear linear differential equation. Let us consider the differential equation y double dash plus p x into y dash plus q x into y equal to r x. If p, q and r are analytic at x equal to x naught, then every solution of the differential equation 4 is also analytic at x equal to x naught and can be represented by a power series in the powers of x minus x naught with a positive radius of convergence. Method of construction of power series. Let us consider the differential equation y double dash plus p x into y dash plus q x into y equal to 0. So, here in this differential equation we are taking r x equal to 0 because the Legendre's equation and the Bessel's equation that we shall be studying later on are homogeneous linear differential equations. So, they are equations of this type. The functions p x and q x are represented in the powers of x r x minus a if the solution in the powers of x minus a is bounded. Now, let us assume a solution of this differential equation of the form y equal to sigma m equal to 0 to infinity a m x to the power m, that is a naught plus a 1 x plus a 2 x square and so on. If we assume that this series can be differentiated term by term, then we get y dash equal to sigma m equal to 0 to infinity m a m x to the power m minus 1, that is a 1 plus 2 a 2 x plus 3 a 3 x square and so on, and the second derivative y double dash is equal to sigma m equal to 0 to infinity m into m minus 1 a m x to the power m minus 2, which is 2 a 2 plus 3 into 2 a 3 x and so on. Now, when we put these values of y dash and y double dash, these expressions for y dash and y double dash are then inserted in the given differential equation. We then collect the coefficients of like powers of x and equate the sum of the coefficients of each occurring power of x to 0. This will give us relations from which we can determine the unknown coefficients which occur in the equation 6 successively. Say, let us take an example, say y dash equal to 2 x y. So, in this equation we will need the value of y and y dash. Y is equal to sigma a m x to the power m given by equation 6, and bi dash is given by equation 7. So, we insert the value of bi and bi dash given by equation 6 and 7 into the given equation and obtain a1 plus 2a2x plus 3a3x square plus and so on equal to 2x into a0 plus a1x plus a2x square and so on. We can then compare the coefficients of like powers of x on the two sides and see that a1 plus 2a2x plus 3a3x square plus and so on equals to 2x into a0 plus a1x plus a2x square and so on. And from this equation, when we compare the coefficients of the like powers of x, we see that a1 turns out to be 0, 2a2 is equal to 2a0, 3a3 is equal to 2a1 and then 4a4 is equal to 2a2 and so on, and thus we get the values of a2, a4, a6 as a0, a0 by 2 factorial, a0 by 3 factorial and so on, while a1, a3, a5 and so on, they are all zeros. Thus, we get the solution of the differential equation as y equal to a0 into 1 plus x square plus x to the power 4 over 2 factorial plus x to the power 6 over 3 factorial and so on, and we can see that the series inside the brackets is the expansion of the function e to the power x square, and so we can write the right hand side as a0 into e to the power x square. Now, next we study the Legendre's equation, the differential equation 1 minus x square into d square y over dx square minus 2x dy by dx plus n into n plus 1 y equal to 0, where the parameter n is a real number, is known as Legendre's equation. It is named after the French mathematician Adrien Marie Legendre from 1752 to 1833. This equation arises in numerous physical problems, particularly in boundary value problems involving spherical configurations. Here now n is a real number. In most physical applications, only integral values of n are required. Any solution of the Legendre's equation is called as a Legendre's function. If we divide the Legendre's equation, that is equation number 9, by 1 minus x square, we will obtain d square y over dx square minus 2x over 1 minus x square into dy by dx plus n into n plus 1 over 1 minus x square into y equal to 0. So, here it turns out that Px is equal to minus 2x over 1 minus x square and Qx is equal to n into n plus 1 over 1 minus x square, when we compare the equation number 10 with the equation number 5. Now, let us note that the functions Px and Qx are analytic at the point x equal to 0, because they are rational functions of x, and the denominator in the functions Px and Qx vanishes at x equal to plus minus 1. So, they are analytic at x equal to 0, and therefore, we can apply the power series method. Let us put y is equal to sigma k equal to 0 to infinity a k x to the power m plus k, where we assume that a naught is not equal to 0 in the equation number 9, and the values of the derivatives of y in the equation number 9. We will have by 1 minus x square into sigma k equal to 0 to infinity m plus k minus 1 a k x to the power m plus k into m plus k minus 1 x to the power m plus k a k x to the power m plus k minus 2. This we get after the differentiation 2 times. Then minus 2x sigma k equal to 0 to infinity m plus k a k x to the power m plus k minus 1. This we get after we differentiate by once, plus n into n plus 1 and then y, that is sigma k equal to 0 to infinity a k x to the power m plus k equal to 0. When we equate the coefficient of x to the power m minus 2, that is the lowest power of x which occurs in this equation, we will get the equation m into m minus 1 a naught equal to 0. This equation is known as the initial equation. This equation tells us that the values of m are 0 and 1, since we have assumed that a naught is not equal to 0. When we equate to 0 the coefficient of next higher power of x, that is x to the power m minus 1, we can see that the coefficient of x to the power m minus 1 will be available only in the first term when we take k equal to 1. The initial equation we had obtained from the first term also itself, that by taking k equal to 0, when we take k equal to 1 in the first term we get the coefficient of x to the power m minus 1, and it will be m plus 1 into m into a1. So, let us put that equal to 0. Now, we put the coefficient of x to the power. The coefficient of x to the power m and higher powers are available in the first, second and third terms. So, what we will do now is that we will consider the coefficient of x to the power m plus k, where k can take values 0, 1, 2, 3 and so on, and put that equal to 0. So, when we find the coefficient of x to the power m plus k in the first term, it will turn out to be m plus k plus 2 into m plus k plus 1 into a k plus 2, and from the second and third terms it will turn out that the coefficient of x to the power m plus k is m plus k into m plus k plus 1 minus n into n plus 1 a k. So, let us put it equal to 0, and we get the recurrence relation a k plus 2 equal to m plus k minus n into m plus k plus 1 m plus k plus n plus 1 over m plus k plus 1 into m plus k plus 2. The numerator, that is m plus k minus n, m plus k plus n plus 1, comes out from here, which this part can be written as m plus k whole square plus m plus k minus n square minus n, and so m plus k whole square minus n square can be factorized into m plus k minus n into m plus k plus n, and then we can take m plus k minus n common. The remaining thing will be m plus k plus n plus 1. So, which the numerator here is m plus k minus n into m plus k plus n plus 1. This is the recurrence relation which connects a k plus 2 with a k. So, if we know the value of a k, we can find the value of a k plus 2. When we take m equal to 0 here, we get a k plus 2 equal to k minus n into k plus n plus 1 over k plus 1 k plus 2 into a k, where k takes values 0, 1, 2, 3 and so on. And therefore, we can find the values of a2, a3, a4 and so on. a2 is minus n into n plus 1 by 2 factorial a naught, a3 is minus n minus 1 into n plus 2 over 3 factorial into a1, a4 after we put the value of a naught, after we put the value of a2, we get a4 equal to n minus 2 into n plus 1 n plus 3 upon 4 factorial into a naught. The value of a2 we have already found here. So, we can make use of that to obtain a4 in terms of a naught. Similarly, we can find a5. a5 is equal to n minus 3 into n minus 1 into n plus 2 into n plus 4 by 5 factorial into a1, where we have made use of the value of a3 in terms of a1 to write a5 in terms of a1. For m equal to 0, from the initial equation it follows that 0 is equal to 0. So, there a1 may or may not be 0. Now, without any loss of generality, we can assume that a1 is equal to 0 in this case also, because the terms that correspond to the case where a1 is not 0, they can be absorbed in the terms which we will get for the case m equal to 1, because they are the same case terms. So, they can be absorbed there, and so the general solution will not be affected, and therefore, in the case m equal to 0, we can, without any loss of generality, we can assume that a1 is equal to 0. And when m is equal to 1, the equation m into m plus 1 equal to 0 gives you a1 equal to 0, and so from the recurrence relation 12, it follows that A2 is equal to minus n into n minus n minus 1 into n plus 2 by 3 factorial A naught. A3 is equal to 0 because A1 is 0. A4 is n minus 3 into n minus 1 n plus 2 into n plus 4 by 5 factorial A naught. A5 is 0 because A3 is 0. So, thus we can say that AK is 0 for all odd k integers, and hence we get the two solutions of the Legendre's equation for the values of m equal to 0 and m equal to 1 as for m equal to 0 we get y1x, the solution by x we call as y1x equal to a naught times 1 minus n into n plus 1 by 2 factorial x square plus n minus 2 into n plus 1 n plus 3 by 4 factorial x to the power 4 and so on. And for m equal to 1 we get the solution y2x as a naught into x minus n minus 1 into n plus 2 by 3 factorial x cube plus n minus 3 into n minus 1 into n plus 2 into n plus 4 by 5 factorial x to the power 5 and so on. Now, when we apply ratio test to this series, infinite series, it follows that they converge for mod of x less than 1. Now, the series that occurs in the function y1x, that series contains only even powers of x, while the series that occurs in the expression for y2x in 14 contains only odd powers of x. Therefore, if we find the ratio y1 over y2, it cannot be a constant, and therefore y1 is not a scalar multiple of y2, and so we can say that y1 and y2 are linearly independent functions. So, a linear combination of the two, that is, we can say that y(x) equal to some constant c1 times y1x plus c2 times y2x is the general solution of the Legendre's equation. Now, let us assume that n is a non-negative integer in the Legendre's equation. If we make this assumption, then one of the two series, that is 13 or 14 will terminate. In the 13th, if n is even, it will terminate, and y1x will reduce to a polynomial of degree n. If n is an odd integer, then the series that occurs in the function y2x, that will terminate and will again give us a polynomial of degree n. Now, a naught, the coefficient a naught that occurs in the functions y1 and y2x is at our choice. So, we can make a suitable choice for a naught. Let us choose it in such a way that the value of the polynomial which occurs in y1 or y2 as n is even or odd has the value 1 at x equal to 1. Then the polynomial will be called a Legendre polynomial, and it will be denoted by p and x. The other series or the other solution, which will be a non-terminating infinite series, will be then called a Legendre function of second kind, and we will be denoting it by q and x. Now, we shall study the Rodrigues formula, which represents the Legendre's function of first kind, that is p and x, by this formula, that is 1 over 2 to the power n into n factorial dn over dxn x square minus 1 to the power n. That is the finite series solution of the Legendre's equation for integral values of n can be expressed in a compact form, which is given by this equation. This is known as Rodrigues formula. So, in order to prove this, let us assume that b is equal to x square minus 1 to the power n. When we differentiate it with respect to x, we find that dv over dx is 2nx into x square minus 1 to the power n. Now, let us multiply these both sides of this equation by x square minus 1. We shall have x square minus 1 into b1 minus 2nx into b equal to 0, if we denote dv over dx by b1. Now, we differentiate this equation n plus 1 times by Leibniz theorem. So, when we differentiate it n plus 1 times by Leibniz theorem, we shall have x square minus 1 into b n plus 2 plus n plus 1 into 2x b n plus 1 plus half into n into n plus 1 2 b n minus 2 n x b n plus 1 minus 2n into n plus 1 bn equal to 0, which after simplification gives us x square minus 1 into bn plus 2 minus 2x bn plus 1 minus n into n plus 1 bn equal to 0. If we set here bn, that is the nth derivative of b with respect to x, dnb over dxn as y, then we shall have x square minus 1 into y2 minus 2x y1 minus n into n plus 1 y equal to 0, which we can see is nothing but the Legendre's equation, whose finite solution we know is given by p n x, and therefore p n x is a constant multiple of b n x, because b n x is dn over dxn of x square minus 1 to the power n. So, when you differentiate x square minus 1 to the power n, which is a polynomial of degree 2n in x, n times you will get a polynomial in x of degree n, and p n x is also a polynomial in x of degree n. So, they must be a constant multiple of each other. So, we have p n x equal to c times b n, or we can write it as c times dn over dxn of x square minus 1 to the power n, where c is some constant. The value of this constant c is found out using the fact that Pn1 is equal to 1. When we had defined Legendre's polynomial, there we had assumed that the constant suitable a naught is so adjusted that the value of the polynomial is 1 at x equal to 1. So, making use of that, we will have Pn1 equal to 1 equal to c times dn over dxn of bn. Bn is x square minus 1 to the power n, we can factorize it as x minus 1 to the power n into x plus 1 to the power n. When we differentiate it n times and put x equal to 1, we will get Vn at x equal to 1. Now, Pn1 is equal to 1, right side is c times. Now, we can differentiate x minus 1 to the power n into x plus 1 to the power n n times. So, when you differentiate x minus 1 to the power n n times, you get n factorial into x plus 1 to the power n, plus then in the next term you will differentiate, making use of the Leibniz theorem, you will differentiate x minus 1 to the power n n minus 1 times, x plus 1 to the power n once, and then multiply by nc1. So, that term will contain x minus 1 as a factor. In the yet next term you will differentiate x plus 1 twice, while x minus 1 to the power n will be differentiated n minus 2 times. So, we will get x minus 1 square as a factor, and so on. So, all the terms starting from second term inside the bracket onwards will have x minus 1 as a factor. Therefore, when we evaluate the term inside the bracket at x equal to 1, it will turn out that its value is 2 factorial into n factorial into 2 to the power n, and thus we shall have 1 equal to c into n factorial into 2 to the power n, giving us the value of the constant c as 1 over n factorial into 2 to the power n, and thus we have the value of the Legendre's polynomial, that is P n x, as 1 over n factorial 2 to the power n into dn over dxn x square minus 1 to the power n. This formula is known as Rodrigues formula, and it is named after the French mathematician and economist Legendre Rodrigues, 1794 to 1851. Now, from the Rodrigues formula, if we find the values of P naught x, it turns out that P naught x is 1, P1 x is x, P2 x is 1 by 2 into 3x square minus 1, P3 x is 1 by 2 into 5x cube minus 3x, P4 x is 1 by 8 into 335 x 4 minus 30x square plus 3, and so on. Now, let us note that P naught x is a polynomial of degree 0, P1 x is a polynomial of degree 1, P2 x is a polynomial of degree 2, P3 x is a polynomial of degree 3, P4 x is a polynomial of degree 4. So, P n x in general is a polynomial in x of degree n and is an even or odd function of x according as n is an odd integer or an even integer. We can see here that when n is odd, that is n is equal to 1 or 3, we have P1 x equal to x, which is an odd function, P3x is equal to 1 by 2 5x cube minus 3x, which is again an odd function, and so on. For P5x also is an odd function, and so on, while P0, P2, P4 they are all even functions. So, Pnx is an odd or even function of x according as n is an odd or even integer. In this picture we see that the P0 x is equal to 1, this is the straight line, P0 x equal to 1, and then we have P1 x equal to x, that is the line, this is the line, P1 x equal to x. Then we have P2 x, this is the parabola given by P2 x, and then we have P3 x, P3 x is this function which we can see that is an odd function of x, and then P4 x is this one which we can see is an even function of x. So, they are the graphs of the Legendre's polynomials for n equal to 0, 1, 2, 3, 4, etc. Now, in general we can write P n x given by the Legendre's given by the Rodrigues formula as sigma k equal to 0 to n minus 1 to the power k 2n minus 2k factorial over 2 to the power n into k factorial into n minus k factorial into n minus 2k factorial x to the power n minus 2k, where this capital N is equal to n by 2 if n is an even integer, and n minus 1 by 2 if n is an odd integer. Let us derive this result by using the Rodrigues formula. By binomial theorem, we can write x square minus 1 to the power n as sigma k equal to 0 to n minus 1 to the power k into n c k x square to the power n minus k, which can be written as sigma k equal to 0 to n minus 1 to the power k n factorial over k factorial n minus k factorial x to the power 2 n minus 2k. Now, put this value of x square minus 1 to the power n in the Rodrigues formula. P n x equal to 1 over n factorial 2 to the power n dn over dx n x square minus 1 to the power n. After differentiating n times with respect to x, the expression for x square minus 1 to the power n will have 1 over n factorial 2 to the power n sigma k equal to 0 to n 1 minus 1 to the power k n factorial 2 n minus 2k over k factorial n minus k factorial n minus 2k factorial. When you differentiate this with respect to x n times, the power of x, which is 2 n minus 2k, will reduce by n and will become n minus 2k, but the power of x is either 0 or it is 1. So, when n is an even integer, okay, this n will be equal to n by 2, and when n is an odd integer, this n will be n minus 1 by 2, and thus we have sigma k equal to 0 to n minus 1 to the power k into 2 n minus 2k factorial, n factorial will cancel, and we have 2 to the power n k factorial n minus k factorial n minus 2k factorial x to the power n minus 2k. The last term is k equal to n, depends on n. If it is even integer, n will have value n by 2. If it is an odd integer, it will have value n minus 1 by 2, because the power of x has to be either 0 or 1. Next, we discuss the orthogonality of Legendre's polynomial. The Legendre's polynomial satisfy an very important condition, that is integral over minus 1 to 1 p m x into p n x dx is equal to 0, where m and n are integers and m is not equal to n. By virtue of this property, the set of Legendre's polynomial is called orthogonal in the interval minus 1 to 1. We know that p m x and p n x are solutions of the Legendre's equation 1 minus x square into p m double dash minus 2 x p m dash plus m into m plus 1 p m equal to 0, because p m is a solution of the Legendre's equation. So, we can write 1 minus x square into p m double dash minus 2 x p m dash plus m into m plus 1 p m equal to 0, and p n x is also solution of the Legendre's equation. So, we will have 1 minus x square p n double dash minus 2 x p n dash plus n into n plus 1 p n equal to 0. Now, let us multiply the equation 15 by p n and 16 by p m and then subtract. We will have this 1 minus x square Pm double dash into Pn minus Pn double dash into Pm minus 2x into Pm dash Pn minus Pn dash Pm plus m into m plus 1 minus n into n plus 1 Pm into Pn equal to 0. The first two term 1 minus x square into Pm double dash Pn minus Pn double dash Pm minus 2x into Pm dash Pn minus Pn dash Pm can be combined to give the following. We have 1 minus x square into Pm double dash into Pn minus Pn double dash into Pm minus 2x into Pm dash into Pn minus Pn dash into Pm can be combined to give the following: d over dx of 1 minus x square into Pm dash into Pn minus Pn dash into Pm. The third term can be factorized to get m minus n into m plus n plus 1 into Pm into Pn equal to 0. Now, let us integrate both sides over the interval minus 1 to 1. We shall get m minus n into m plus n plus 1 integral over minus 1 to 1 Pm into Pnx dx equal to minus 1 minus x square into Pm dash into Pn minus Pn into dash into Pm evaluated at x equal to minus 1 and 1. When we put x equal to 1 and minus 1 in the expression inside the bracket, the value of this is 0. So, we shall have m minus n into m plus n plus 1 integral over minus 1 to 1 Pm x into Pnx dx equal to 0. Now, if we assume that m is not equal to n, then we can divide by m minus n into m plus n plus 1 and we will have the result integral over minus 1 to 1 Pmx into Pnx dx equal to 0. However, when m is equal to n, now when m is equal to n, we will not be able to divide by m minus n in the previous equation. Therefore, we will have to find its value separately. It turns out that when m is equal to n, the value of the integral minus 1 to 1 Pm into Pn x dx, that is minus 1 to 1 Pn square x dx is equal to 2 over 2n plus 1, where n takes values 0, 1, 2, 3 and so on. Let us derive this result. By Rodrigues formula, we know that the 2n into n factorial Pnx is equal to nth derivative of x square minus 1 to the power n. So, making use of that, n factorial into 2 to the power n whole square integral over minus 1 to 1 Pn square x dx is equal to minus 1 to 1 dn x square minus 1 to the power n into dn x square minus 1 to the power n dx. Now, when we integrate the right hand side by parts, if we integrate it once, what will happen is that we will have integral of dn x square minus 1 to the power n, which will give us dn minus 1 x square minus 1 to the power n into dn of x square minus 1 to the power n. When we will evaluate its value at minus 1 and 1, it will be 0, because dn minus 1 into x square minus 1 to the power n will contain x square minus 1 as a factor. So, after integrating it once, we will have its value as minus integral over minus 1 to 1 dn minus 1 x square minus 1 to the power n into dn plus 1 x square minus 1 to the power n dx. When we do this integration by parts n times, the right hand side will become minus 1 to the power n integral over minus 1 to the integral over minus 1 to 1 x square minus 1 to the power n into d2n x square minus 1 to the power n dx. We will have 2nth derivative of x square minus 1 to the power n here, and here there will be no derivative of x square minus 1 to the power n, which is equal to minus 1 to the power n integral over minus 1 to 1, and then d2n of x square minus 1 to the power n will give us 2n factorial, because x square minus 1 to the power n is a polynomial in x of degree 2n. So, when we differentiate it 2n times, we get 2n factorial into x square minus 1 to the power n dx. Now, this is equal to 2 times 2n factorial integral over 0 to 1 1 minus x square raised to the power n dx this is obtained on multiplying x square minus 1 to the power n by minus 1 to the power n, which gives us 1 minus x square to the power n. And then since 1 minus x square to the power n is an even function of x, so using the property of definite integrals, integral over minus 1 to 1 can be written as 2 times integral over 0 to 1 minus x square dx, x square raised to the power n dx. Now in this we put x equal to sin theta, and then we see that integral over minus 1 to 1 pn square x dx becomes 2 into 2n factorial over n factorial into 2 to the power n whole square into integral over 0 to pi by 2. The limits of integration change from 0 to 1 to 0 to pi by 2. 1 minus x square to the power n becomes cos theta raised to the power 2n, and dx is cos theta d theta. So we will have cos theta raised to the power 2n plus 1 d theta. Now we make use of the gamma function in order to evaluate this integral. Here the power of sin theta is 0, while the power of cos theta is 2n plus 1. So using the formula integral 0 to pi by 2 cos sin theta raised to the power m cos theta raised to the power n d theta equal to gamma m plus 1 by 2 gamma n plus 1 by 2 over 2 times gamma m plus n plus 2 by 2. We have evaluated the value of integral 0 to pi by 2 cos theta raised to the power 2n plus 1 d theta as gamma n plus 1 gamma half over 2 times gamma n plus 3 by 2, which is multiplied by this coefficient 2 into 2n factorial over n factorial into 2 to the power n whole square. Now it comes out after we expand the gamma functions, it comes out to be equal to 2n factorial, gamma half is root pi, n factorial 2 to the power n minus 1 into 2n plus 1 2n minus 1 and so on 3 1 into root pi. Root pi can be cancelled, and then we can expand 2n function 2n factorial function, and we will have 2 over 2n plus 1 here. Next we consider the generating function. The function, we will see that 1 minus 2xz plus z square raised to the power minus half can be expanded as sigma n equal to 0 to infinity p n x into z to the power n. So the coefficient of z to the power n in the expansion of 1 minus 2xz plus z square raised to the power minus half gives us the Legendre polynomial p n x, and thus we can call this function as the generating function. When we expand this function in the powers of z, the power of z to the power n gives us the Legendre's polynomial p n x, or you can say the Legendre's function of first kind. So it may be called as a Legendre generating function. Let us consider the expansion of this in the powers of z. Let us first write the expansion of 1 minus t to raised to the power minus half by binomial expansion. It can be written as 1 plus 1 by 2 t, 1 by 2 into 3 by 2 over 2 factorial t square, 1 by 2 3 by 2 5 by 2 over 2 factorial t cube, and so on. We have used binomial theorem here, and then 1 plus half t, 1 into 3 by 2 factorial 2 square t square plus 1 3 5 over 3 factorial 2 to the power 3 t cube, and so on. We can expand, write it like this, and which can be further written in a convenient form as 1 plus half t plus 4 factorial over 2 factorial square 2 to the power 4 t square, then 6 factorial over 3 factorial square 2 to the power 6 into t cube, and so on. And therefore, let us put now t equal to z into 2x minus z. We will get the expansion of 1 minus 2xz plus z square raised to the power minus half as 1 plus half z into 2x minus z plus 4 factorial over 2 factorial square 2 to the power 6 z square 2x minus z whole square plus this is n minus k plus 1th term, and then we have this n plus 1th term here. Let us collect the coefficient of z to the power, let us collect the terms in z to the power n in this expansion. Now the terms in z to the power n will occur only in the term containing z to the power n 2x minus z to the power n and the previous terms, because after this term we will have the power of z as n plus 1 and the power of 2x minus z as n plus 1. So, the least power of z will be n plus 1. So, the coefficients of z to the power n will occur only in this term, that is z the term containing z to the power n into 2x minus z to the power n and the previous terms. The term in z to the power n arising from the term in the second line of equation 12 is, in this equation if you find the coefficient of z to the power n, it turns out to be 2n minus. Now, the terms in z to the power n which arises from the n minus k plus 1th term of the equation 17 is given by 2n minus 2k factorial over n minus k factorial square into 2 to the power 2n minus 2k into z to the power n minus k, and then n minus k c k into minus z to the power k into 2x to the power n minus 2k, which after simplification gives us minus 1 to the power k into 2n minus 2k factorial. Then we have 2 to the power n into k factorial, n minus k factorial, n minus 2k factorial, x to the power n minus 2k into z to the power n. Hence, the terms in z to the power n are, and the terms in z to the power n are sigma k equal to 0 to n capital N minus 1 to the power k 2n minus 2k factorial over 2 to the power n into k factorial n minus k factorial into n minus 2k factorial x to the power n minus 2k into z to the power n. Now, this coefficient of z to the power n, as we have seen earlier, is nothing but the Legendre's function of first kind, that is Legendre's polynomial p n x. So, we get p n x into z to the power n. Here we may recall that the value of this capital N is small n by 2 if n is an even integer, and the value of capital N is n minus 1 by 2 if n is an odd integer. And thus, we can see that the expansion 17 may be written as 1 minus z into 2x minus z to the power minus half equal to p naught x into z to the power 0 plus p 1 x into z to the power 1 and so on p n x into z to the power n and so on, which can be written as sigma n equal to 0 to infinity p n x into z to the power n. And by for this region we can call 1 minus 2x z plus z square to the power minus half as the generating function of the Legendre's polynomial. Now, let us take an example on this. Let us prove the recurrence relation. N into p n x is equal to 2n minus 1 into x p n minus 1 x minus n minus 1 p n minus 2 x. This result is known as a recurrence formula, because from here if we know the Legendre's polynomial p n minus 1 and p n minus 2, we can obtain the value of p n x. So, in order to establish this result, we shall make use of the Legendre generating function of Legendre's polynomial, that is 1 minus z into 2x minus z to the power minus half. We know that this is equal to sigma p n x into z to the power n. When we differentiate this with respect to z partially, we will get minus half into 1 minus z into 2x minus z to the power minus 3 by 2 into minus 2x plus 2z, while the right hand side will become sigma p n x into n z to the power n minus 1. After simplification, this equation becomes x minus z into 1 minus z into 2x minus z to the power minus half equal to 1 minus z into 2x minus z into sigma n p n x into z minus z to the power n minus 1. We have multiplied after simplification this equation by 1 minus z into 2x minus z also, to make the power of 1 minus z into 2x minus z as minus half. And then we make use of this generating function for Legendre's polynomial. We can write this equation as x minus z into sigma p n x into z to the power n, and then 1 minus z into 2x minus z into sigma p n x into z to the power n minus 1. Now, let us equate the coefficients of z to the power n on both sides. So, left hand side the coefficient of z to the power n will be x minus z into Pn, that is x Pn x. The coefficient of z to the power n will be x into Pn x, and then on the right side when we take the coefficient of z to the power n, we will have n Pn x z minus 2x into n Pn x, and here we shall have the coefficient of z to the power n will be n plus 1 into Pn plus 1, because when you multiply this by 1 you get n the coefficient of z to the power n as n plus 1 into Pn plus 1. So, we get n plus 1 into Pn plus 1, and left side the coefficient of z to the power n will be x into Pn x, and then here the power of z becomes n plus 1. So, z to the power n coefficient will be Pn minus 1. So, we get x into Pn x minus Pn minus 1 x, Pn minus 1 x, while the right hand side gives us n plus 1 into Pn plus 1 x, and then minus 2 n x into Pn x. This we get from here, minus 2 x into n Pn x, and then z to the power n. The last term is plus z square multiplied to this. So, that makes the power of z as n plus 1. So, the coefficient of z to the power n will be n minus 1 into Pn minus 1 x, and after simplification this gives us n plus 1 into Pn plus 1 x equal to 2n plus 1 into x Pn x minus n into Pn minus 1 x. Now, when we replace n by n minus 1 in this equation, we will get the required result. Now, we will discuss the associated Legendre's equation. The associated Legendre's equation has applications in potential theory. Let us see how we arrive at the associated Legendre's equation. If we differentiate the Legendre's equation, 1 minus x square into d square y over dx square minus 2x dy by dx plus n into n plus 1 by equal to 0 m times with respect to x, and write u equal to dm y over dxm, that is mth derivative of y with respect to x, we shall have this equation 1 minus x square u double dash minus 2m plus 1 x u dash plus n minus m into n plus m plus 1 into u equal to 0. We arrive at this differential equation after we differentiate the equation 18 m times by Leibniz theorem and make use of u equal to dm by over dxm. Now, if we put v equal to 1 minus x square to the power m by 2 into u in this equation, then it becomes the following: 1 minus x square into d square v over dx square minus 2x dv by dx plus n into n plus 1 minus m square over 1 minus x square into v equal to 0. This equation is known as associated Legendre's equation, and it has applications in the potential theory. It occurs frequently in potential problems. And now, we see that v is equal to 1 minus x square raised to the power m by 2 into u. So, and u is m dm by over dxm. So, v is equal to 1 minus x square to the power m by 2 dm by over dxm, and therefore, the solutions of the equation 19 are 1 minus x square to the power m by 2 dm over dxm Pn x and 1 minus x square to the power m by 2 dm over dxm Qn x. Pm x, we know that Pn x and Qx are the solutions of the Legendre's equation. So, these are known as associated Legendre's functions. They are denoted by Pnmx and Qnmx. In the potential problems, the equation 19 and its solutions occur in terms of the trigonometric function x equal to cos theta. So, let us put x equal to cos theta in the equation 19. The equation 19 we can write alternatively in this form: d over dx of 1 minus x square into dv by dx plus n into n plus 1 minus m square over 1 minus x square into b equal to 0. So, now if we put x equal to cos theta in this equation, we shall see that we get the following: 1 over sin theta d over d theta sin theta dv over d theta plus n into n plus 1 minus m square over sin square theta into v equal to 0. Or we will have this d square b over d theta square plus cot theta dv over d theta plus n into n plus 1 minus m square cos square theta into v equal to 0, and hence its solutions are sin theta raised to the power m into mth derivative of p n cos theta over d cos theta raised to the power m, and sin theta raised to the power n dm of cos q n cos q theta over d cos theta raised to the power m. If we put m equal to 0 in this equation, if we put m equal to 0 in this equation 20, then we shall get the trigonometric form of the Legendre's equation. In our next lecture, we shall discuss the extension of the power series method, that is the Frobenius method, and with the help of the Frobenius method we shall find the solution of the Bessel's equation, which again has lots of applications in the applied mathematics. Thank you.